Okay, the direction of the induced EMF. The direction of the induced EMF is such as to oppose the change which produces it. In other words, we've got a coil here. So you wrap this wire around it, like that. Okay, we can put a little resistor there so the current can flow. Now, as the magnet comes towards it, let's say that's north and south, then there's going to be an increasing field heading into the coil. Okay, so what's going to happen there is the coil is going to create an EMF and hence a current that will set up a magnetic field to oppose the one coming in, or one that's increasing. So the north pole is coming in, so this coil is going to create a current in such a way that there is a north pole opposing it, and the direction of that current, you'll use your right hand grip rule with your thumb pointing to the right, and it shows your fingers coming over the top from underneath, and so the current is going around this way. Now in this one here, as the magnet is coming towards it again, in this one here, let's ignore that part and make it going to the right. So ignore that, like that. Okay, we've now got the magnet moving to the right, and we'll have north again here, south again there, and the coil that we had before with a resistor back there. So now this one, we have got a north pole moving away, and that means there's a reducing magnetic field as the magnet's been pulled away. So what's going to happen is the coil is going to set up a magnetic field in such a way to oppose that change, so it's going to try and keep the magnetic field there. So in other words, it's going to get a magnetic field in the same direction. So north and south, the same direction as the other one, to try and keep it there, or to oppose the motion. So this one's moving to the right, so it's going to try and attract it back. However, before, this one was moving in, so it tried to repel it back. Okay, so it's opposing that motion. And so the direction of the current given by your right hand grip rule, whoops, because it's going this way. Now what we're going to do is place two coils side by side on a soft iron core. So let's have one coil here and another one. Okay, this one will have a battery switch like that, and this one here will have a resistor and maybe some sort of ammeter or something like that. So what is observed when the switch is closed? Well, currently with the switch open, there is no magnetic field. However, when this goes closed, there is going to be a current going around the coil that way, creating a north pole at this end, south pole at that end, and initially the voltage will be 0, and then it will increases to some other value, and it's not instantaneous. Okay, there is a delay. There is time to change, and during that time the magnetic field will be increasing. So this is coil on this side is going to try and create an increasing magnetic field through this one. Now the one on the right, let's call it number 2, is going to create a magnetic field to oppose that change. So this one is going to create a south pole at this end and a north pole at that end to oppose it. Okay, and that means a current going in the opposite direction. So that's what's observed when the switch is closed. What is observed when the switch is opened? Okay, in that case, the current, so we're now opening it here, okay, so the current will now be decreasing over time to 0, and so it takes time. So this south pole at this end is going to get weaker, and so what's going to happen is this magnetic field is going to try and keep it there, so oppose the weakening of the magnetic field. It's going to try and keep it there, and so that means it's going to create a current in the same direction. So the current swaps direction.